Welcome back, everyone, to the second session of CATMO 2020. This session is going to be on optimal control, among other things. It's been a very exciting conference so far, and one of the things I really appreciate about the conference has been the morning sessions, which is a kind of a nice chunk of things to think about and then sleep on it, and then we can come back ready to discuss again the next day. So the first session, the first talk will be by Jessica Cunningham, who has been working on translational math models at IMO at Moffitt for the past 10 years or so, including, of course, the adaptive therapy, and more recently, publishing a nice review on the parallels between integrated pest management and cancer control. And today she will be talking to us about optimal control in castration-resistant prostate cancer, which I believe was just published, right?
Yes.
So yeah, take it away, Jessica. Go ahead.
All right, let's see if I can share my video, if you all want to see me. All right.
There you are.
Okay, so yeah, so this paper, this is actually a paper, and it serendipitously got published literally yesterday at 2 o'clock in the afternoon. It's on PLOS ONE, so you can find it if you're on Twitter. I did a tutorial about it, which was pretty entertaining. So there's lots of ways to get at this. So I'm excited to just kind of talk you through it. It'll be kind of short. I hate to say it to you, but this is yet another analysis of the prostate cancer model that was used for the clinical trial back in 2017. Let's see if I can, hello, there we go. So we've been talking a lot about adaptive therapy, and I've been thinking about it and thinking about that particular model for almost 7 years. And you just kind of get, you get into rabbit holes about it. And one of the rabbit holes that started really early with some of the super original analysis was, of course, why did we pick 50%, right? So why did we pick the 50% drop? And it's relatively arbitrary. So, the more that you look at these models and the more that you talk about them, why not drop only 20%? Why not drop only 1%? Why not drop at all? Why not drop the PSA at all? That's the extreme interpretation of adaptive therapy. And dropping the PSA 0% is basically stability. So polymorphic stability, meaning some resistant, some sensitive cells, hopefully happens. This is a huge if. This is one of my most theoretical papers, which is fun. So can we actually get these true stability, true actual constant stability in vitro or in vivo? There's some evidence of it. It's very little evidence. So just keep that in mind, that this is a thought experiment maybe at this point, but it's a very fun thought experiment. So can we actually get a polymorphic stability in vitro and hopefully in vivo? Who knows, but let's pretend that we can. So we can hope. So the way that you can get these stability points within these types of models that we talk about, and especially in the Zhang et al. Model, and Rob and Yannick have talked about this a lot as well. And this talk actually, this paper came from that Leiden conference about a year ago as well, where Yannick again was kind of the one driving this. So the competition coefficients kind of have to be greater than 1 in order to get stable polymorphisms that don't kill you, basically. So there's a lot more math about that in the paper, and you can go there to find it. And there's some evidence that this is probably maybe possible. Again, a lot of this is, the caveats go on for days, so maybe I'll just stop doing that. So we have some in vitro analysis from Audrey's paper, which should be hopefully maybe coming out. It's on bioRxiv, where we did Lotka-Volterra equations, matched it to competing cell types, and we see these pretty high competition coefficients, as high as 12. And then also from the analysis that Bob showed on Monday, where we're trying to kind of match the clinical data, the best sort of full cohort matches suggest that these competition between sensitive and resistant cells are quite high, so definitely greater than 1. Now, the original model, our assumptions were, and they were safe assumptions, to assume that these competition coefficients were between 0 and 1. And this was just a great way to start. So what I did with this paper was throw that assumption out the window. And instead, because of some of this results in vitro, maybe some of it in vivo, just raise some of these competition coefficients. So again, in the paper explains exactly theoretically why we chose to raise that one competition coefficient from 0.9 to 2. That's actually the competition of the sensitive TP cells, so the producer cells on the resistant T- cells. So all we did was just from 0.9, we bumped it up to 2 and did a whole bunch of stability analysis. The figure on the left, these are kind of, this shows the stable equilibria. Now, the stable equilibria, they exist. There's stable equilibria that exist when the competition coefficients are less than 1. But unfortunately, the total tumor volume has to be higher than a carrying capacity of any single cell. So the carrying capacity of any single cell is 10,000, and these stable equilibria happen at greater than 10,000. So in this model, we would kind of assume that you'd either be dead at that point, or this is an unacceptable, we can argue about what carrying capacity means, but those stable equilibria are not clinically possible. But if we have these competition coefficients that are a little greater than 1, what we start to see is these stable equilibria start to exist within a situation where the total tumor burden is not killing you. So we picked an arbitrary value, 9,000. Obviously, you could pick 5,000, you could pick 2,000, whatever you want to do. And the trade-off between how high that competition has to be in order to get a low enough stability point, a low enough tumor burden for stability point. So at 2, we still have to have that stable, we still have to have that maximum tolerable tumor burden up at like 9,000. Now, if it was 10, we could drive it down to say 5,000, these sorts of things, something to think about. So now, magically, theoretically, in magical, mystical, spherical cow land, we have these stable points. So this would be great if this really happened in vitro, in vivo. I'm not sure if it does. I hope it does. I think that'd be fascinating. But the real question is not if they exist. Theoretically, we can make them exist. I can make anything exist with this model, basically. But the real question is we have abiraterone, and can we use this single drug to arrive at and stay at these stable equilibria? And not only just can we get there, but can we get there from anywhere? So a lot of the models we talk about are very frequency dependent. We only talk about the frequencies of these 3 types of cell types. Here we have to include the density. So the best way I could think to plot these was on this 3D graph. So the number of T+ cells is the x-axis, number of TP cells is the y-axis. So the x and y are these sensitive cells that are affected by abiraterone. And then the z-axis shows the resistant population. So what I did was we made 100 random patients that are within this under 9,000 total tumor burden. So the sum of xt plus TP and T- is less than 9,000. And we picked 2 stability points. In the paper, I think we picked up to 9. So there's a whole bunch, huge supplemental, go to town if you really want to look into it. So the question is, no matter how you come in, so we don't know the composition of a tumor when a patient comes in. We have no idea. We can take a single biopsy of a single metastasis, but that doesn't really help. So I kind of just wanted to assume we were as dumb as possible. And we just made 100 random patients with these tumor compositions of any kind. So how can we move these patients towards these stable equilibria just using abiraterone? All right, fancy, fancy math. I used something called the forward-backward sweep, which is a numerical optimal control technique. And the answer is titration. Yay, who knew? I didn't know. I had no idea that that was what was gonna pop out. And when you start to look at it, it starts to make a little bit of sense. So if a tumor has a stable point, and I have no idea if that's true, regardless of which one it is, and you'll see in the paper even up to all the other stable points with different competition matrices, titration seems to be the way to get there. And the reason that is, and these are actually all the trajectories through this space. So this patient started with a high number of sensitive cells, but really not that many resistant. And it's kind of hard to follow, but they all kind of like sweep up and then come down. And again, go to the paper. It's really cool to really think about, how this is traversing this space and how you have to manipulate all of the moving parts of the different densities in order to really hone in on that stable point. Now, we don't win all the time. So these red lines, these ones that are highlighted in red, they actually crossed that 9,000 total tumor burden. So they would have died while trying to get to the stable point using titration. So this doesn't always work. Interestingly, I started to look up titration and obviously this is very common in a lot of other drugs where they're using like antidepressants, treatment of diabetes, these sorts of things. You're trying to find that optimal dose, that minimum effective dose, right? How do you find this minimum effective dose? And there's some things that use ramp up toxicity to try and minimize toxicity, and there's other ones that use ramp up titration to minimize financial toxicity. But what's really cool is there's been these two studies, and the references are in that paper, where there might actually be some clinical hints that something is going on using titration. And they were using titration to try and deal with financial and physical toxicities. But maybe there's something in it about this, stable equilibria, and I don't really know. So it's very exciting that there's some clinical hints that this is successful. So that's optimal control land, and that's magical and mystical, where we know everything about everything. We know where we started, we know where we're going, we know exactly what the space looks like. we're magical magicians of knowledge. Okay, that's not how clinic works at all. So what can we do with no information? And no information is basically the clinic. So I tried to make this as dumb as possible. Can you do this pretty much blind? So I came up with some pretty dumb stabilization protocols to kind of test this out. So obviously we're going to compare to maximum tolerated dose, which is giving abiraterone full. I'm going to compare it to the clinical trial protocol, cutting by 50%, and then these stabilization protocols. So, and this is a really interesting talk, especially after Hitesh talked about, what is the volume you should stabilize at? And I think that that's a completely unknown question. And many have talked about that higher is better, and this will show again that higher is better. But these three protocols try to stabilize at the incoming tumor volume. So these patients, I made 10,000 of them this time, patients that are lower to this left corner have really tiny tumor volumes, while patients up on this boundary have really, really high tumor volumes. So this is trying to stabilize at whatever the patient comes in with. And then these two are trying to stabilize at whatever this maximum tolerated tumor volume is. I made it up, I picked 7,000, you can pick whatever you want. That's high, but not really high, or maybe it is, I don't know, to be determined. And basically all we did was just a dose, just a dose scheme where if the tumor is starting to grow too much, you bump up the dose. If the tumor is starting to shrink too much, you bump down the dose. And this is all we did. So then I threw 10,000 patients at this really dumb stabilization protocol that either started at maximum tolerated dose and titrated down, or started at 0 dose and titrated up, and then the 2 different volumes. So there's a lot going on here. But this is kind of fun. This is just another visualization of what we think we're really doing here. So maximum tolerated dose is bad. We kill all the sensitive cells and we start to fly up this resistant, axes where no matter where you start, we get rid of all the sensitive cells and we die up here. Now, adaptive therapy, the dropping by 50%, while better, we're really kind of dancing around this, we're really spiraling up towards the same place that maximum tolerable dose gets. So while it's better, it's still kind of missing the point, right? We're a little bit too aggressive. We're a little bit too, aggressive, I guess is the right word. Now, with the titration protocols, you can start to see how it's a little bit different. So if you start at maximum tolerable dose, all the time, all these protocols were like, oh God, we're doing too much, and titrated down really fast, and then kind of tried to find this sweet spot where it was stabilizing this tumor volume at the incoming tumor volume. And in this particular patient, you just really can't do it. we kind of killed a lot of the sensitive cells, the resistant cells are coming up. So what if we increase that tumor volume that we attempted to stabilize at? So instead of 6,000, all we did was bump it to this 7,000. And you actually save this patient. So the dose titration says, oh my God, stop giving maximum tolerable dose. We actually get all the way down to giving none at all until that tumor volume comes back up to this maximum tolerated tumor volume, whatever that is, and then kind of dances around until we kind of stabilize at this stability point. So starting up high is okay, but this is risky. So it's actually better to assume don't treat at all first. This did a little better, but you can see that even though we've stabilized the tumor volume, we're actually losing the game underneath. This is probably what will happen clinically. But in a magical mystical land, you can titrate up until you start to see, okay, we're losing the game. We got to bring this back into control. Okay, we're kind of here. And then now we're really stabilized. And you can see that path in here just sort of comes in and spirals right to the spot. So I ran so many patients, it's a lot. All kind of just looking at who lives and who dies and how this really comes together. And you can see, again, maximum tolerable dose, we just kill everybody. Adaptive therapy does okay. And some of these other dose titration do okay. But the best one still is starting at no dose and ramping up only when you have to, and stabilizing at the maximum tumor volume that you can. There's a lot of analysis in the paper of who lives and who dies. So there's a lot of caveats with titration. We overtreat a lot of patients still, and we also undertreat a lot of patients. So this is who lived, the initial tumor compositions who lived. So maximum tolerable dose, nobody lived. Now, what's interesting in adaptive therapy is it really only saves the patients that already have a really high tumor burden and pretty low resistant cells. But if you do this minimum dose titration, you can really save all of these patients with low tumor volumes because you're allowing them to grow quite large, and you can tolerate these higher resistant populations by, manipulating those sensitive cells to come back. Now, the problem is that there's still a lot of patients that are left that have sensitive cells in them that die. So while we're overtreating some, this titration can tend to also undertreat by not treating enough, and you get close to that threshold, and then the patient dies while you were trying to ramp the drug up. So, these dose changing things are pretty tricky, but it's kind of fun. So conclusions, I guess I'm already talking too long. I could talk about this for days. So theoretically, an increasing dose titration could provide a benefit beyond this standard adaptive therapy where we're trying to do these up and downs, right? We could potentially implement this with little to no additional information. This is kind of what that would look like, where we're letting the PSA rise, the quality of life of the patient is okay, and we're not treating at all. Now, the minute the quality of life drops, you say, okay, this is a not okay PSA. Maybe we should try to stabilize here, maybe here. I don't know. So you start to ramp up the drug, and then you start to play that game of trying to stabilize. So when we reject this cure, we have to really replace our definition of success. And in these types of models, the quality of life while having tumor in you becomes paramount, and that's terrifying. And a lot goes into that. And while maximum tolerable tumor burden is theoretically ideal, I'm sure that minimum containable tumor burden would no doubt be clinically ideal, but I don't know how to find that. So that's up to this whole group of wonderful people here to help figure out. Obviously, there's a ton of questions. So I love this quote, the purpose of models is not to fit the data, but to sharpen the question. I love this, it keeps me sane. So you guys can stare at these questions. A lot of them have come up already in other talks. Hitesh will love the first one. Is PSA good enough? Probably not, but it's what we got. CTCs would love it. There's so many other things we can measure and we just don't. What about cancers without biomarkers? Can we use imaging? I loved Jill's talk. A lot of this stuff only works if there's really competition going on. So what happens if you have resistant lesions and sensitive lesions? Does any of this work at all? What is this maximum tolerable tumor volume? Do we have to write an IACOC protocol for humans? This is a terrible idea, but maybe we should. How often do you make treatment decisions? Intermediate doses? Are we creating new monsters? And I think this is the real big question is, when you stabilize something long enough, something else nasty is going to pop up. Whether it's a new mutation of some kind or cachexia or more metastasis, it's an interesting question of how long can you really keep this going. And my favorite is like the psychological implications. So would you do this if you had cancer? And I don't know what my answer to that question is. So thank you. There was a lot of work that went into this. Yannick is here at this conference. So is Joel, Bob, and Katerina. Dr. Zhang, I always thank because he was brave enough to try this in patients in the first place. And then Frank and Ralph are at University of Maastricht, who were very helpful in coming up with the theoretical analysis for this. So thank you.
Excellent talk. Yeah, I'm looking forward to reading the full paper as well. We have a few questions, probably only time for one, maybe two questions. Yeah, no problem. It was a great talk. The first question would be from Renee Brady. Is it possible to determine the maximum tolerable volume for individual patients? Have you identified specific parameters that are driving that threshold?
Yeah, that's a clinical question. I mean, in every model, no, I won't say that. In many of the models, especially here, higher is better. Now, clinically, that's going to be patient dependent. Some patients have PSA values. They come in and they're 10,000, and they're not as sick as somebody with a PSA value of 10. So this goes back to how useful is PSA? I'm not really sure. So I really think that we have to have better measures of quality of life that are not completely dependent on having no tumor burden. So a lot of our clinical discussion of cancer is have as little as possible. And I think we have to just start having that conversation of how do we start measuring, are you okay right now with what tumor you have? And that'll come along with pain, that'll come along with what the physician is willing to do, what the patient is willing to do. These sorts, I'm not sure that's a theoretical question so much as truly a clinical, personal, psychological question. Yeah.
Right, good point. Okay, so there are a few other questions, and I'm going to encourage Jessica to maybe answer those in the chat or during the discussion session.
Yeah.
So in the interest of time, we'll move on.